Hi, good morning. I want to introduce chapter 23, and for today's part, I will just talk about the induced EMF and magnetic flux and Faraday's law of induction, and what is related is Lenz's law. Just these two, and hopefully you can bring all your questions to class after the spring break. Okay, let me start from here. By the way, this discovery was by accident. Like he was doing Faraday was doing some work, and then he found that there was a current created in this circuit when the switch is closed. Then you can see here that is we have kind of a coil here, and that was able to find that there is a magnetic field that was creating a current. This is the reason why we talk always about that relation between electricity and magnetism. Like electricity can bring magnetic field, and magnetic field can bring electric currents. Now, there is, I will say, a current that is going to be induced in that circuit, and this is really, we call it induced because it's not an actual, okay? And I will say, when we close when we close the circuit, we're gonna have the current induced in one direction, and when we open the circuit, we're gonna have the current induced in the opposite direction, and we'll study why it's the opposite. Now, the conclusion here is that if there is a change in the magnetic field, which means if I would say the current was stable in the circuit, like it did not change, no induced current will be created. But if there is a change, which means the current is growing or the current is dying, then there is a change in what is called the magnetic flux, which creates a current. Now, also here there is a demo, and of course I provided also with 3 videos that they're gonna explain to you what's going on here. You can see here that there is a bar magnet. This is the North Pole, this is the South Pole, and then when I am bringing in that magnet, I push that through the coil, we are going to have a current that is going to be induced. If I have the same orientation here that the north, but I am bringing the magnet away from the coil, we are going to find that we are going to have a current that is reversed. The same is going to happen when I will have the South Pole facing the coil and pushed in, and then we're going to have the current in this direction. When I am bringing the South Pole away, the current again is going to be reversed. Now, if I have no motion between the coil and the magnet, this is going to be the case when I will not have any any induced current in the circuit. Something that we need to know, that the change in flux can be made through what we did before, like opening and closing the circuit, or by bringing a magnet in or out. And in all the cases, what we are looking for is we are changing the magnetic flux, and what the change in the magnetic flux is the one that is going to create that induced EMF. A very important, let's say, I will say, application is going to be the electric generator, where we have a coil that we will use mechanical energy to move it. Now we use, of course, natural gas, that is gonna create steam, and the steam is gonna drive that generator, or any method that we are going to use. And we have a magnetic field here. Then by making that motion through the magnetic field, we will be able to create electric current. And mainly I will say that EMF that is going to be induced here, it depends on rotation rates, like how fast you are going to make that rotation, and other factors, and we will discuss this in details throughout the chapter. Maybe you did hear me talking about what is called magnetic flux, and that magnetic flux, it is defined, we give it a phi, and that is the strength of the magnetic field times the area times cosine theta. And cosine theta is gonna be between the vector, which is A, the vector of A and B. Now vector A, it is always perpendicular to any area A. Then basically what we are trying to find here, the angle is between A as a vector and B, the magnetic field. Any change in the magnetic flux phi increases an EMF. Then like change means decrease, or in a decrease, and we call that electromagnetic induction. Now, of course, apparently based on the equation, the magnetic, electromagnetic flux, I will say the units are really Tesla times meters squared. Now, Faraday's law and Lenz's law are really very related. I will say the EMF depends on the change in the flux. EMF is greatest when delta T is short. EMF is inversely proportional to delta T. And of course, I will say N, which is the number of turns. Then EMF equals minus N, the change of phi over the time. This is, we call it Faraday's law of induction, and it is used to calculate the EMF, which is in negative N delta phi divided by delta T. Okay, I'm gonna make this video very short. I'm gonna go back to you with another video. For this one, I'm gonna stop now, and then I'm gonna continue later.